We have an exam next week. It's Tuesday, 1 week.
It's 27th or 29th?
Tuesday, 29, right? Yeah, did I say 27?
No, 29th.
29. Yeah. So 1 week from today.
Yeah.
Yeah. And we'll have another homework due on that day too. But that's, yeah, can have everything that we covered until today can be part of the exam, but the homework is due either on the exam day or let's say on Thursday. Right? We should check. Or maybe here is how I'll put it. I will not completely ignore the problem, but the chances are high that it will be less emphasized, like less than 20 or less than 20% will be on this homework, or less than, let's say less than 10%. So do the homework. It's just to encourage you to do the homework on a time, but at the same time, it's not completely relevant. Okay, because then special relativity, everything comes together in one piece. It's one topic. So our idea was that we wanted to discuss Maxwell's equation without the static approximation. Like earlier we did electrostatics where time dependence was killed completely. And in the process of dealing with electrostatics and or electricity and magnetism together, we came across the idea of special relativity. We spent a good deal of time there. And now it is clear to us that electric and magnetic field transform, but there is a tensor which are scalars, which are invariants. So how do we work with electromagnetic field in general? Or most importantly, the first piece that, or the most fundamental concept we studied long ago with almost in introductory physics is the electric potential due to a point charge. Right? And what is the electric potential due to a point charge?
1 by 4 pi
1 over
4 pi q by r.
Yeah, q by r, right? So there's a distance dependence and charge over distance, basically. That's the electric potential. Very good. And now we would like to see if we bring in time dependence, how does this change? This was electrostatics. If you have a point charge sitting at the origin, that's your q over r. If you were to have time dependence, how does this change? How does this electric potential change? And that's going to be our primary goal. And that's the Green's function, remember. 1 over our electric potential is nothing but the Green's function. So we want to find that Green's function for a moving charge. So broadly, we will call this retarded Green's function. So this, let me not say, at this point, let's just say Maxwell's equation. Maybe I will say what is in a moment. Maxwell's equations again. So we have L dotted with epsilon naught E is equal to rho, right? Everything is time dependent. Let me at least write it in one equation. Or T, and that's rho of R T. And del dot E is equal to 0. Del cross E is equal to minus time derivative with respect to P, and del cross what do you call this? D over mu naught, yeah, H or B. Like I like to write it as H. Yeah, let's write it as H. So del cross H, that's equal to time derivative of D, which is yeah. Yeah, let me write this in this form. Plus G, right? I like to write this as D, this as D. Okay. So that's your Maxwell's equation, but we want the Green's function associated with this. So let's proceed. And we know that this immediately implies that B can be written as a curl of the magnetic potential. This was the case in magnetostatics, but this is still the case. Like even in a complete Maxwell's equation, this is still valid. So this is still true. So that's going to be our first relation. And once I have this, I put this back in here. So put this in here. And I learned that del cross E plus, like I take it on the left hand side, del cross dA by dt is equal to 0. So that's the second equation I have, which means that the curl of the electric field plus the time derivative of the magnetic potential is equal to 0. And curl of something being equal to 0 means that this can be written as a gradient, right? Earlier what we had is in electrostatics, we said del cross E is equal to 0. If del cross E is equal to 0, then immediately you say that electric field is equal to gradient of phi. But now that's not the case. Now we have this plus this as the curl. So this implies now that electric field plus dA by dt is equal to negative gradient of the potential. So we still can write it as a potential, but now there is an additional piece. So what we have is that, so together we have two conditions. One is electric field is negative gradient of phi minus dA by dt. And the magnetic field is equal to curl of A. Let's put this back in and let's see what other equations governing our electric or our potentials. Okay. So that's going to be our goal. So let's put this equation, let's say, what should we put it in? Let's start with maybe this equation. Which one should I? Yeah, let's start with fourth one. Yeah, okay. So del cross. This is where it is good to now write it as B because I have B is equal to del cross A, right? So this is B is del cross A, and that is a mu naught, right? And mu naught, I'll take it on the right side. That's mu naught times epsilon naught d by dt of electric field, which is minus del phi plus dA by sorry, minus plus mu naught times G. So I multiplied by mu naught so that this becomes the magnetic field. E. So this can be expanded out exactly like magnetostatics. So this is gradient del A minus of del square, the Laplacian of A, and that's equal to, we recognize this as the speed of light. So it is minus 1 over c square, second derivative of time, the magnetic potential, and we have plus mu naught J. And this cross term also. So this is minus 1 over c square d by dt of gradient. I think I got all the pieces. Okay. Let me write this as, take the time derivative on the left side, take this on the right side. Del square plus okay, so that takes care of these two terms. And let me write this as mu naught times J. This takes care of this. And now let me put this on the right side. So this is minus the gradient, which is common on the both. So this is del divided with A. And I have minus, there's minus I've taken common, so it's plus 1 over c d by dt, and this is phi over c. I split the c square in both ways because remember phi over c had this relativistic, it is a fourth component of A. So that's one thing. If you remember your magnetostatics, if the time dependence was not there, you would have, this wouldn't have been there, this term wouldn't have been there, this term wouldn't have been there, and this is your gauge.
Yes.
Right? This is your
Coulomb.
Coulomb gauge, right? So that's your Coulomb gauge, and that's how it shows up. But now we will have a Lorentz gauge. So we want to have this plus this to be the 0. So Lorentz gauge allows you to do. So this is del divergence dotted with divergence of A plus 1 over c d by dt of phi over c is equal to 0. But remember that this is it, and this is Lorentz gauge, and this is slightly different in the sense it's a covariant gauge. In what sense is this covariant? Whenever it's a covariant, we can write it as a 4 vector times 4 vector. Right? That's what it means by covariant. So remember your relativity that A mu is equal to phi over c times the vector A. In fact, that was expression, and d mu was 1 over c d by dt on gradient. So if you write d mu a mu, that's a covariant object because it's the dot product of two 4 vectors. And that's nothing but notice this is 0, 0. Already it is aligned, so I don't have to change any sign. Typically, I have to change signs if I'm doing both 4 vectors. Since it's already one is covariant and one is contravariant, I don't have to do that. And this is 1 over c d by dt phi over c plus divergence of A. And that's set equal to 0. So our Lorentz gauge, which is a covariant gauge, means we knew mu is equal to 0. And if that's the case, this whole term drops out, and I just have this equal to this. And this is a nice equation. This is a wave equation. Right? If this was equal to 0, that's a wave equation, and that's good. So if I set this to using the Lorentz gauge, this whole thing goes away. Okay. So we'll come back to that. Let's go back. So this led to the magnetic potential. This equation led to the electric potential. This leads to the expression for the magnetic potential in terms of current. Finally, we are remaining with the Gauss's law, which will give us the electric potential in terms of charge. So let's see how it works. So we go back and say divergence of the electric field is epsilon naught times electric field is minus L phi minus dA by dt, and that's equal to rho. And let me remove the epsilon from here and write it at the denominator here, which is the same as mu naught c squared rho. Correct? Because 1 over mu naught epsilon naught is c squared. Okay, so that's equal to minus, again, expand this out, del square phi is equal to, I'm leaving some space, I'm going to put this together quickly. So this is mu naught times c squared times rho, and take this piece on the right side. So this is plus gradient d by dt. So gradient of it. Okay. I want to add and subtract on both sides so that I get this wave equation. So this is 1 over c square plus d square by dt square by 5. I want to add this so that it looks exactly like this. So I have to do the same thing on this side, but I do that as I have d by dt already out. So then I have 1 over c d by dt of 5 over c. And again, that's nothing but the Lorentz gauge on the right side. That's identical. So this is equal to 0 in the Lorentz gauge. This term goes away. So that's very similar equations we have for both the electric and magnetic potential, but now with time dependence in taken care of. So this is a full electromagnetic equation, if you will. So again, so this is minus square plus 1 over c square electric potential phi of RT is equal to mu naught c square rho of T, and right as epsilon naught, 1 over epsilon naught. That's how it is. And this is mu naught times J. Again, if the time dependence was not there, we get back our electrostatics and magnetostatics if you take away the time dependence. The Green's function then will be, so now we define our retarded Green's function. This is called retarded, and we will, retarded means this is delayed a little bit. So the main idea is that if the charge moves, the effect of that at a certain observation point takes some time to know. Like for example, today, if you say that if you write a letter which goes by snail mail, by the usual old postal ways, and if it has to reach Chicago, it will take some 1 day to reach there. And if your friend has to know what is happening with you, that is a delay of that. So that's retardation. So it's a retarded effect. So if you say that I'm coming to Chicago, they know about it only after a day. So that's the retardation effect. So everything is delayed by speed of light. So that's a name coming in. So this is called retarded Green's function. So the electric potential, which we know as 1 over R, now we want to retard it in the sense we want to have the effect of speed of light to come into it. So the Green's function is constructed by removing the function we are interested in and putting a delta function at only one point in space, and in this time at one point in time. So our retarded Green's function will be defined by this equation. And G is having both position and time. So this is R, that's your observation point, and that is a source point. R prime is the source point, and T is the observation point in time, and T prime is when the source existed. And this is delta Q R minus R prime, and that's delta of T. So the way you want to imagine this is, if T part was not there, that's your point charge, right? That's electric potential point charge at R prime creates an electric potential at R. But now we say that an effect due to the electric potential at time T, because of the presence of the potential at T prime. So the charge, this is T prime is the charge's time, and this is observation time. So that would be a difference. The main idea is that if T is less than T prime, it shouldn't know about it. If the charge did not exist, then it doesn't exist. So we want to take care of relativity and all the causal features in there. So that's what we want to solve. Again, it's clear that if this was not there, time was not there, there should be the static electric potential should show up. To solve for this, what we do is we do it in the frequency space. This is time. Let's work in the frequency space. So go to Fourier transform this. So G of R prime T minus T prime is equal to only the time part we are going to Fourier transform. So that's going to be minus infinity to plus infinity d omega over 2 pi e raised to minus I omega t minus t prime, and the Fourier transform of G. Typically, I do not differentiate between them, but it should be different. But here in this in today's lecture, I have differentiated. It is tilde, that's just helpful reminders. And this is frequency dependent. So this is the frequency dependent Green's function, Fourier transform, and this is the time dependent. If I know this, I can integrate this and help it. So that we want to solve for that. If I want to get the equation for the Fourier transform to Green's function, it's very straightforward that put all the time derivatives with I omega. There is a nice prescription that replace all the time derivative with minus I omega and replace all the delta functions with 1. Right? That's what that's how you go from position space to momentum space, or in this case time space to frequency space. So and actually G going to G tilde also. So make these changes and you will be you will get the equation for G tilde. So then our equation becomes L square plus, that is a minus I omega, minus and a minus. When I square this, gets positive. I square is minus 1. So this is minus omega square root square. Tilde or minus r prime omega is equal to Q or in the frequency space, this is, we are saying that there are so many signals that go at each one with a special frequency. But when we stick to a single frequency, it's expected that things will be spherically symmetric, right? It should not matter whether for a particular frequency, whether I'm looking at this side or that side of the universe. So this should be magnitude of R. So we are going to use spherical symmetry now. So use spherical symmetry. To argue that R minus R prime is pretty much, it depends only on the magnitude. Right? That's what happens with a point charge also, right? It's 1 over R, which is the distance between the source and the observation point. And let's also keep the source at the origin so that this can be replaced with R. Magnitude of the R. That's for simplicity alone. Otherwise, we have to carry this baggage of this, and not just simplicity, it gets pretty, or yeah, simplicity, a significant simplicity, they see way more work to do it at an arbitrary point. We'll have to use special functions there. When we want to return back, we will get our answer in terms of R. When I want to put it back, I just have to replace R with R minus R prime, and that should be our solution. Right? So let's write our equation in terms of this. So we have, let me go to the next code. So let me expand this out. Gradient Laplacian in spherical coordinates is 1 over R squared d by dr, R squared d by dr, minus 1 over R squared sine theta d by d theta sine theta theta, and there is one more term, minus R squared sine squared theta d squared by d phi squared. That's your Laplacian and spherical coordinates, minus omega squared over c squared. And I'm already using the fact that I'm at the center of the, I keep the source at the center. So the G tilde doesn't depend on angular coordinates, right? It just depends on R. There is no theta phi, so that is no theta, no phi. And it depends on omega. Right, and that's equal to the delta function. So the delta function in spherical coordinates is R delta of theta del J of phi. That's your 3 r theta and phi. But since I need the dimensions correct, so this is a delta function always comes with it with the element, a line element for each of this coordinate. So we had to supply that, and this will be r square. One is r and one is r sine theta, so this is r square sine theta. So that's a line element of the wall. You can say that's a volume element, scale factors basically that comes in. There is no angular dependence in theta and phi, so this goes to 0, right? And this goes to 0 because this operator doesn't have anything to operate on, so that simplifies things significantly. So I have minus 1 over r square. Actually, r square can cancel out, right? But let's keep it. R square d by dr minus omega square of c square, and tilde. This is just r and omega is equal to delta r square sine theta. There is this angular delta function on the right hand side. That's not convenient, so let's integrate it out. We don't want any angular structure, so let's just integrate out theta and phi. So let's integrate from 0 to pi sine theta d theta and 0 to 2 pi d phi. So this side, so this is minus 1 over r square d by r tilde r omega, and do the same thing on the right side. Theta 2 pi d phi or theta pi r square sine theta. That's just a trick to get rid of this delta functions, which is clear because sine theta goes away now. And once the sine theta goes away, the delta function is just 1, right? Or not 1, 1, right? Because they replace theta with whatever exists, but there is no theta dependence, there is no phi dependence. So on the right side, this is simply delta of r over r square. On the left hand side, there is no angle dependence in all this, so this whole thing comes out. And this gives you a factor of 2, and that gives you a factor of 2 pi. So total 4 pi, right? That's the angular integration that you have. So our equation then becomes minus 1 over r square d by dr r square d by dr minus omega square over c square. That is a factor of 4 pi. I put it down here, and g tilde or omega. Okay, that's your equation. Let's take a small so at this point, let's actually go and see how does this work for the static case, right? This should lead to the static case. If I want to go to the static case at this stage, how will you go? Like, how will you go from here to the static case? Is the question clear?
In this equation, there is no time difference.
Yeah, there is no time dependence. Omega?
Yeah,
Why omega 0? That's a correct answer over there. Why do you say frequency equal to 0 is time independence?
It's not evolving.
Because this is the first mode.
Yeah, I mean, think of this as omega is 2 pi over t, right? Very simple, naive way. And if that is so, you're breaking all the time dependence into many oscillations. If there is no time dependence, that is equivalent to saying that the time period is infinite. Right? The oscillation happens, but it is happening in infinite time. So that is time period is 0. So that means no, time period is infinity because you're saying it happened for a long time. So that's omega. So the static case, which we mean by time independence, if you wanted to see that in the frequency space, that will be contained in omega equal to 0. So that's the connection between the two. So that means when I set omega equal to 0 here, I should get back my static. Okay, so let's see how that happens. So let's go to static. Okay. Just for learning purposes and more than learning experience, like we want to see some boundary conditions. So static case is omega equal to 0. And that's 1 over r squared and d by dr and r squared d by dr, and this is g tilde of r0 now. Right? The static case is got by omega equal to 0, and that's delta of r over 4 pi r squared. Again, r square cancels out. So I have minus. So now we are in the static case. We know the answer roughly, right? So, and what is the g tilde r of 0? What is it? No, this is a static potential, right?
Yeah, I mean,
So R, there is only R dependent. We know that this is 1 over 4 pi R. Right? There is a charge there, but now this is a delta function. So charge is 1 basically. Green's function is the electric potential due to the unit charge. And epsilon naught is not there because in the equation, when we put it inside this, epsilon naught will show. So that's a 4 pi R scenario. So we know that answer, but let's try to derive this from here for a moment. Okay. Okay. So r square cancels out. So this is d by dr r square d by dr tilde r comma 0 is equal to delta r over 4 pi. Again, whenever there's a delta function, it's good to integrate. It gives us some conditions on the function at least. So let's see what happens if you integrate R, remember, is a spherical coordinate. This is less than infinity and it's greater than or equal to 0. Integrate there. So this is minus 0 infinity dr d by dr, and this is r squared by r times d tilde times r is equal to 1 over 4 pi, so 0 to infinity dr delta r over 4 pi. And this might be bothering. Okay, how do you do a delta function integral when you're really going from 0 to infinity? Like this is right on the edge of the integral, right? Delta function has to be in between. So you have to go back to Gauss's law, right? So this is, you say, oh, I don't trust this, this is not convenient. You would like to say this is equal to 4 pi, 1 over 4 pi, which is correct, but you, at this stage, one might even doubt this. So you can go back all the way to this point, right? So that you bring in all the spherical symmetry in here. So if you go back and put the spherical symmetry, put the omega square in that, that's your Gauss's law. If you want it, G tilde is equal to delta Q. Let's say R, right? Say R. Right. That's the same equation, except that I undid all the angular case, which is necessary here, but I'm just motivating that this is equal to 1 over R. And at this stage, again, when you integrate here, then you say that, okay, I want to do this integral instead of going from 0 to infinity. This time I will do a volume integral. My source is at the origin. Again, I do the volume integral here, dqr. And this time it is clear that this will be equal to 1. Here it was slightly confusing because it was going from 0 to infinity. You would have worried that, oh, the delta function doesn't really come up at the boundary. But this is a spherical coordinate. And in this case, it is clear this is a Gauss's law now we are using. And in this case, it is even better because now you can write this as dA dotted with gradient of G tilde. Right? And this is a closed integral. From here to here, you used divergence theorem. And you say that, okay, what is the solution for this? This is equal to 1. And using Gauss's law, now you immediately conclude that G tilde has to be equal to R, 0 has to be equal to, that is a 4 pi because this gives you a 4 pi there. Yes.
So how did you get rid of the minus sign?
Oh, how did I get rid of the minus sign? No, I did not want to get rid of that. This is minus. Yeah, this is minus sign. Sorry. There is this minus sign. And why do you need that? Because gradient of 1 over R has a minus 1 over R square. Right? So that minus sign cancels that. And the 1 over R square cancels the area element here. The typical Gauss's law. Because that's the electric field, right? Electric field is positive. Electric potential is also positive. So negative of that gives you the electric field. So that's the same thing as electric field is negative gradient of the electric potential. Right? That's the negative sign. That's the sign. So it is there, and then this will be equal to -1. So overall, what we are saying is that this is nothing but 1 over 4 pi times R minus R prime. And I jumped a few steps, one can go this in more detail. In fact, it is necessary that that has to be that form because otherwise you won't get that delta function on the right side. Okay, one can do this more formally and properly in few more steps. But let's go back here, and that means that this is equal to 1 over 4 pi R, and this is at G of R0, right? Not okay, is that clear? Okay, any questions at that stage? Okay, so again, our strategy is going to be, we are interested in retarded Green's function. That's what our goal is. We went to the Fourier space, so we started solving for that. And we said, okay, even that is tricky. So let's make this spherical symmetry where R. And now we are looking for that R omega. And we just checked that at omega equal to 0. In a sense, it's a condition. We know that at omega equal to 0, it should have this form. So when I want to come back after I solve this equation, I put that here, replace R with R minus R prime, do this integral, and I'll get back my complete retarded Green's function. So I have to trace back all the steps. But at this stage, this is a one-dimensional differential equation, and I will be able to solve this. Okay. So let's try to solve that. So our equation again is minus d over dr r square d by dr minus omega square over c square times g tilde or omega is equal. So that's our equation that we have, and we have a condition that at least we have learned that g tilde are of 0. Not even learned, we just know this, that this is 1 over 4 pi r. So let's guess this. It's not really guess. This is an unknown. I can always write the unknown in terms of another unknown. Right? So let me write this as g tilde of r omega over 4 pi r. So let me I write it in this form because that's the 0, right? At omega equal to 0, this should give you this. That means that implies that g tilde of r0 is equal to 1, right? Because this is 0, that's the 0, that's equal to 1, that gives me this. So let's write our equation for g tilde instead of capital G tilde. Let me write this for g tilde. Let's just substitute this, right? I have to take the derivative. So d by dr of g tilde is equal to, it hits two places. I can write minus 1 over 4 pi r square times g tilde, or I can hit the actual plus 1 over 4 pi r times derivative of g tilde. So that's the first derivative. Multiply it with r square. That's minus g tilde over 4 pi plus r over 4 pi times d by dr of g tilde. Another derivative, d by r square or g tilde, because I want to substitute that, writing that equation in terms of small g tilde. So that's the same as, now there are two terms. One is minus 1 over 4 pi times partial derivative of g tilde. I can hit this, that gives me plus 1 over 4 pi times d by dr g tilde, or I can hit this final piece, which is plus r by 4 pi and second derivative of g tilde. Conveniently, this cancels out. So our differential equation then becomes, put this all in there. R floating around. Yeah, because that R probably will cancel. Yeah, okay. So this is minus of this. So this is minus r over 4 pi second derivative of r square minus omega square over c square times g tilde over 4 pi. Oh, I have to do one more. I should have started with that. No, what am I doing? So this acting on G tilde is this. So this is minus R over 4 pi. Second derivative of R square G tilde. And there is minus omega square over C square. This is a capital G tilde, which is nothing but G tilde over 4 pi R. And there is a delta function on the right side, and that's not what I want. Where did I mess up? Did I miss something? Was that? Oh, this was an R square. Oh, this was an R square, right? Oh, no, but I canceled the R square. No, but I cannot cancel the R square, right? Yeah, because this is not correct, right? So there should be an R square here, there should be an R square there. I cannot cancel that because this one doesn't have an R square. So this is R square, and there is an R square. Agreed? Yes. And then I will get a, so then I do this the same way, this the same way. This I will put a 1 over R square everywhere on the corner. That's 1 over R square. These things goes through. There is 1 over R square, 1 over R square, that will balance out. And this becomes 1 over R square. And that tells me this is 1 over R. So 1 over R square. Yeah, I think so. So it's still not satisfied. But this is 1 over 4 pi R now. There's a minus sign. Oh, 4 pi R cancels here. Yes, good. This is G over 4 pi R. It's G over 4 pi R. And here it is 1 over R square for some reason. Yes. Well, that's what it is. Yeah, okay. Yeah. So I can cancel away the 4 pi R and see that this is equal to minus second derivative of R square minus omega square over C square times G tilde of R omega. That's what we're trying to solve for. And that's equal to delta of R over R. And we just have this condition that it should satisfy 1. Whenever we have a Green's function, which has a delta function, there is one, these are the general solution for this is constructed out of the points when r is not equal to 0. Like when r is not equal to 0, then the right hand side is 0, right? And that's a simple differential equation. So let's have that part coming out, and from that point on, it will be easier. So let's set r is not equal to 0. If r is not equal to 0, then we have the differential equation minus, we make it plus, right? E of square g tilde is equal to minus omega square over c square times g tilde. So we will be able to get the solution everywhere other than r equal to 0. But r equal to 0, we know that there will be a delta function because even for the static case, it's there. It's kind of a symbol thing. But in general, not very trivial. If we have this differential equation, what's the solution you can say? Solution to that equation?
Exponential.
Exponential, very good, right? Exponent and oscillatory exponentials, like not the decaying exponential, oscillatory sine and cosine, which is exponential. So g tilde of r omega is equal to, it could be plus or minus a times exponential I, is omega over c times this is dimensionally correct? Yeah, 1 over time. And it's just omega, right? No, but this is r. Yeah, correct. So this is r. So this is omega times r and plus b times exponential I omega over c. Am I saying this? Yeah. Distance over time is speed. Yeah, dimension is. Okay. So that's your solution, if you want. There is a restriction to this because we said that at omega equal to 0, it should be equal to 1. So set omega equal to 0. So this is r0, that's equal to 1. That's equal to a plus b. So we have a condition here that a plus b has to be equal to 1. So that's pretty much our solution, but now we are traced back. I said that once we have the solution, we have to put it back in this to put it back in that, and then do the integral. Right? Get back, trace back our steps. And we will also see where, I mean, this seems to be a little arbitrary, right? There is still an independence of one variable, right? So we'll see what that is very soon. So put it back. So this is, so that's our solution with a plus b equal to 1. Put this back and here. So our Green's function in the frequency space is 1 over 4 pi r. So it is a over 4 pi r times exponential of I omega over c times r plus b over 4 pi r times exponential of minus I omega over c r, with the condition that a plus b has to be equal to 1. That's all restriction we have on that. Clear? Put this back. No, one more thing. We said this was spherically symmetric. We want to put this back into, replace r with r minus r prime, right? We can trace back those steps. So then we have g tilde r minus r prime of omega would be equal to a over 4 pi times r minus r prime times exponential of I omega over c, right? Again, r in the exponential, this is r minus r prime. Plus b over 4 pi r minus r prime, and exponential minus I omega over c times r minus r prime. Let's do a simple check. Is what is G tilde? Very simple check. This should be true. 0. That's a static case. The exponential goes away, and we have a plus b over 4 pi r minus r prime, which is indeed equal to 1 over. Right, so it satisfies the case that static case is. So this is our frequency, our Green's retarded Green's function in the frequency space. So you want to now put this in the time space, right? Do the inverse Fourier transform, and we should get that. And for that, we have to do this integral. That's the integral we have to perform for that. So let's do that. Back and back here. So if I know this Green's function, I can get my total the primary Green's function in the time domain. T minus T prime is equal to that's equal frequency integral 2 pi minus infinity to plus infinity minus I omega T minus T prime, and put this whole thing in there. So it's a over 4 pi r minus r prime times omega over c r minus r prime plus b over minus I. That should be clear. But notice this is a frequency integral. If a over r doesn't actually depend on any frequency. These are two integrals. A over 4 pi r minus r prime times an integral that goes from minus infinity to plus infinity, the omega over 2 pi. These two exponential have omega in common. It's exponential minus I omega, like this as t minus t prime from here, and this is minus omega over c r minus r prime. So this is t minus t prime I omega minus omega, also no omega. So 1. Let's see. And dimensionally, distance over velocity has the dimensions of time. There's one more integral. So let me write that as here, b over 4 pi r minus r prime. And this is minus infinity to plus infinity, d omega over 2 pi exponential plus I omega, or again, minus I omega, so to say. And this is this time t minus t prime plus 1 over c r minus r prime. Okay. What is that integral equal to? a definite integral. It's an exponential. It should be straightforward integral. But what is that integral equal to? I've seen this before. Okay.
I have seen it before.
Yeah, but yeah, try to do it. So, what is this integral? How about this? Minus infinity to plus infinity d omega over 2 pi exponential minus I omega t. It's a simple exponential integral, but a very tricky integral. Hmm? No, there should be no omega, right? After this integral, omega should be all gone. There should be only time dependence. But then you have to take the limit, right? Omega tends to infinity and plus infinity. So if you notice, if you were to set t equal to 0, here, then the exponential is gone. That's infinity. Right? And if t was not equal to 0, this is oscillatory, sine and cosine, and they kind of cancel out. You can argue that. Again, very clean argument, but that's 0 and infinity. But that should be familiar. What is that? Delta function, right? So this is basically a delta function of time. So whenever you see an exponential integral with frequency, whatever is there in the argument, that whole thing becomes a delta function. So this whole thing is a delta function. So what is the solution? So this is the actual retarded Green's function we're talking about. So we have a over 4 pi r minus r prime, which is a static Green's function. This whole thing is a delta function. T minus t prime minus 1 over c r minus r prime. Another piece plus b over 4 pi r minus r prime, except now this delta function is t minus t prime plus 1 over c r minus r prime. So there is this, so this is t. So there is this charge somewhere here at r prime, correct? This is r prime at the source. That's your observation point r. Something happens at t prime. And you try to observe this at time t. Right. And what is this? This seems to be a time. What is this time? This is the time taken to, so this is t is equal to distance over speed, right? So that means this is the time taken for light to go from here to there. Right? So if you notice, the observation time is delayed a little bit. Like this is your source time, observation time. And there is a delay of how much time the light takes to go from here to there. So this t is t prime plus this r minus r prime over the speed of light. That's the retardation, right? This is behind by a certain point. But what is this? This is t prime plus something. This is in the future, right? So there's slight arbitrariness here. So let's look at this slightly more carefully. So observation time t. So this contributes whenever this is equal to 0, right? So this contributes at t prime plus 1 over c r minus r prime. Right? So this is the observation time. Observer, that's your source. And delta function means that this, you have to set this to 0. So that means this is the time when you will observe this. This observer will observe something happens at t equal to 0, and after about 3 seconds, you will see the observation. What that second term is telling is that observation time is before the source time. Right? This is before the source. Right? That's not possible. So this is causal. This is not causal because the observation time is before the source time. You have to subtract that. At t equal to 0, something happens. But at t equal to minus 3 seconds, someone observed whatever happened at t equal to 0. Right? So this is not causal. Is that clear what I'm meaning?
Yeah.
That's not allowed. That we cannot, or we don't see this in reality. So this is, you have to impose this. So you set, so you set b equal to 0. Because mathematically it is allowed, but we don't want it because we don't see, we only see causal behavior. So you set b equal to 0, which immediately sets a equal to 1. Because a plus b is equal to 1, so it implies that a is equal to 1. So our retarded Green's function then is r minus r prime t minus t prime is equal to 1 over 4 pi. That's your static Green's function times a delta function. How does the time dependence work in the Green's function? It works by pointing out that the observation point is causal and it will know about what is happening whenever light reaches it. So something happens at the source, it takes some time for light to reach there, and then you observe. Right? That's a simple statement of the new potential. This is electric potential, remember. So whatever was 1 over r, now you are modifying it with this causal behavior or the retardation in time. And that will be our starting point. And now we can start moving things. We will talk about a charge moving, and there is an effect here, what will happen at the further point. And most of often these problems get tedious to work with, but some problems, for example, when the uniform speed, that becomes very tractable. And another point that becomes tractable is when you go very far away. When you go very far away, that's called the radiation. Those problems becomes very easy to deal with as far as you're not very close to the source. If you go at a very far observation point, then you can deal with that. And that's what we deal with antenna. Right? Antenna is the observation point is very far away from the antenna. So our new electric potential is this. That's a time dependence in the electric potential. Okay, I'll stop here.